Hi there. So we will now continue with our discussion. So we are now in module 3 of this course. So for this part, we will be discussing mathematics in communication. So for the first part, we have coding theory. Okay, so what are the problems that we have in coding theory? So um, we want to send data from one place to another through a channel, and then it may yield error. So what we want to do is first we want to detect if an error occurs, if an error occurs, and the second one is that we want to correct these errors once they are detected. Okay, so let's look at first this. Let me see if you can read this passage. From there, what is that? It takes a great deal of courage to stand up to your enemies, but a great deal more to stand up to your friends. So this is from Harry Potter. So as you can see, your brain is a code cracking machine. It doesn't matter. So for example, again, it doesn't matter what order the letters in a word appear. The only important thing is that the first and last letter are in the right place. The rest can be a total mess and you can still read it without a problem. So there you go. Even if the letters are all jumbled, you can still read it without any problem, right? Okay. And then similarly, your mind is treating this automatically without even thinking about it, correct? So even if, again, it's just automatic. Your brain can decode something which is supposedly hidden. Okay, so this is the model for in communication. You have your sender, and then it will pass through a channel, and then of course the receiver. But I guess all of you have already played the pass the message game, right? And most of the time is that the message sent by the sender, when it goes to the receiver already, the last person in the line, it's already a different message. And why is that? The culprit behind it is the channel, right? Because the channel, in this case, you have only one person, but most of the time you have two or more people who would be the channel, right? So there's noise and then there's problem with the channel. Okay, now let us first define what is coding theory. We already used that term before, but what does that really mean? Coding theory deals with the design of error-correcting codes for the reliable transmission of information across noisy channels. Take note, you have noisy channels. Okay, so we want to detect and correct the errors in the transmission across these noisy channels. Again, the problem is we have here a more detailed example, more detailed. So we have the message source, and then the source encoder, the channel, the source decoder, and the receiver. I will talk about source encoder and source decoder later on in detail. But then again, you have your sender and then you have your receiver. Again, here are the two goals. We want to detect and to correct error. Okay, so for example, you have this message, "Hi Rob." Okay, so when you put it in numbers, we turn that into bits, either 0 or 1, and then somewhere along the line, okay, something happened, and then instead of "Hi Rob," it became "Hi Joe." Alright, so for example, we have these two messages, yes and no. Yes is transmitted as 00, and no is transmitted as 11. Now, um, so for example, here you have yes is transmitted as 00, but because of noisy channel, it became 10. So in this case, we do not know if it's really 00. So in this case, we do not know if it's 00 or 1, 1. So if it's 0, 0, this one had an error. Or if it's 1, 1, we do not know which one has an error, this one or the second digit. Imperfect transmission of data. So as I've already mentioned before, um, we send messages through noisy channels, and messages are usually transmitted in the form of binary strings, zeros and ones. So some causes of the imperfect transmission of data is probably sometimes an electric surge, so cross-contamination from another data stream or human error. Okay, it can easily change some of the zeros to ones and vice versa. So this is an example of a human error. So due to a typing error, Saturday story on local artist John Henninger mistakenly reported that Henninger's bandmate Eric Liddy was on drugs instead of drums, right? So because of this letter here, G and M, so that's human error. And also you can have, as I have mentioned a while ago, you can have electric surge. So another noise, okay, so in information media such as communication systems and storage devices of data, they are not absolutely reliable in practice because of noise or other forms of introduced interference. Okay. Application. So take note, for example, when you take pictures in outer space, so you use error control codes to protect the data against noise that can be caused by atmospheric interruptions. So how were the pictures taken? So the picture is divided into many pixels, and each pixel has a varying degree of brightness. And this degree of brightness is represented by a string of zeros and ones. And then of course, again, we want to make sure that the message is correct, so that the varying degree of brightness would be correct, so that we have the correct picture. So also for compact discs, I don't know if you already if you encountered CDs. So take note that a CD player can still read data from a CD even if it has some scratches. But of course, if the scratches are, just very deep, the CD player will not be able to read it. It will not be able to correct the error. It can detect an error, but it can no longer correct the error because there has been too much damage done on it. So also for computer networks, so we want to make sure that we also want to transmit the right data. And also for telephone lines. So as you can see, or even in your mobile, so coding theory is applicable everywhere. We might not, in this course, we will not know for exactly how it works, but at least it will give you an idea. Okay. First, let's look at the terms that we need to understand. Source coding. What is source coding? Source coding is changing the message source, such as data terminal or the human voice, to a suitable code for transmission through the channel. I will show you later the ASCII code. Okay, so anyway, the point is from your text, you want to encode it, okay? So that's the one that you will transmit. So here you have your source encoder. So it transforms the source output into a sequence of symbols, and usually that's zeros and ones, that we call a message. So for example, this is our source encoder machine. So the source input is go, and then after going through the machine, okay, it translates it as um, 101, and this is now your message. What is a code word? A code word is a string of zeros and ones which represents an actual message. So for example, we have stop, it is encoded as 00, go as 101, wait as 110. Now these three terms over here are your code words. The rest that you do not see here, like 100, 111, Okay, they are not code words because they do not mean anything. Unlike these three, they mean something. Okay? The length of a code word is the number of the binary digits it has. So for example, all of these code words have a length equal to 3. Okay? Now when we collect our code words and we form them in a set, we call them your code. Okay, so in the previous slide, we mentioned that these are your code words, and when you collect them in a set, that is now your code. What do we mean by the word encode? Encode means that the message becomes a code word. So again, in our example wherein go is transmitted as 101, we say that the source encoder encode the message. Obviously, that's why it's called an encoder, because it encodes the message. To decode means the reverse of the encoding. So the received word is reverted back to a message. So of course, if I receive 101, I want to know what that really means. So you now go through your source decoder or the machine that decodes it, and then after it passes through this machine, you will now know that it means go. Okay. Let's now take a look at some codes. So this is just one of the this is part of your 7-bit ASCII code. Okay, so here, so it's represented, so I just have here your vowels, some of the letters, and then some of these consonants. Okay, encode the message SAT. Alright, so let's look at that. So when we encode that, SAT S is, so for S, that's 1010011, this one, okay? And then A, so that's 1000001, and then lastly T, so that's 1010100. Okay, so that's how you encode SAT. What about this one? Decode this. Okay, so um, I had it color coded for you so that it will be easy for you to look at it. Okay, 10, 10, 0, 11. That's this one. B. No, that's S. 100101. This one. That's E. And lastly, 10, 10, 10, 10, 100. Where is that? T. Okay, so to decode, that is the word set. Alright, next we'll go to parity check codes. First, let us define what do we mean by parity. A bit string is said to have an odd parity or even parity depending on the number of ones in the string. So for example, in this case, we want to count the number of ones. We have 1, 2, 3. We have 3 ones. That's an odd number. So that's why we say that it has odd parity. For this one, we have how many ones? 1, 2, 3, 4. It has 4 ones. So therefore, it has even parity. Parity check digit. Okay, so the simplest form of error detection is parity, wherein a single bit is appended or added to a bit string. The idea is to have a code with only one parity, and usually that parity is even, although it doesn't have to be necessarily even, just usually. Okay, so we remember what we want to do is we want to append a single bit or a single digit, okay, so that all of the words in our code will have one parity. Okay, so for example, include a parity check digit to make an even parity code. So for example, yes, we want to add one digit. But since we want it to be even, okay, so therefore, what should this be? This should be 0, so that we have no ones at all. So that's even parity. Now, in this case, what will we append? We have 3 ones here, but we want it to be even. So this becomes 1. Okay, so that we have an even parity code. All right, so suppose you have this one and then it was transmitted as 010. You can now easily detect that there is an error. There is an error because this one has odd parity. Now take note here that you were able to detect the error. You were not, I'm sorry, you were able to detect that there is an error, but still the problem is, how do you correct the error? We still do not know if it's 1111, which is no, or 000, which is a yes. Okay, we do not know. Okay, so let's try this. Append one bit to each word to form a binary word. Again, we want it to be of even parity. So we have how many ones here? We already have 6 ones. So this one should be 0. So that you still have 6 ones. This one you have 1, 2, 3. That's odd. So we have to add 1 to make it even. 1, 2, 3. Again, that's an odd number. So we have to add 1. What about if we want it to be odd? So 1, 2, 3, 4, 5, 6. We want it to be odd, so this one would be 1. So this is just the opposite of everything of the last slide, right? This second one should be 0 because this is already 3 ones. And this one also 3 ones. So we just append 0. Now, one more. We want to append one bit to make an odd parity code. So this one should be 0. This one should be 1. And lastly, this one should be 1 so that it would be odd. Now, suppose that the binary word received is 1010. Again, we are talking about odd parity here. So that's why we know that there is an error because this one has even parity. Now, what about repetition codes? So in repetition codes, we repeat each bit a certain times so that we obtain, so for example, we want, this is the intended message, 1010. So what you do is you repeat this 3 times. So you have there 0 is repeated 3 times, 1 here is repeated 3 times, and lastly, the last digit is repeated 3 times. So that's what we mean by repetition code. So try this. Encode the bit string by repeating each bit thrice. So let's have 0 here. So 1, 2, 3, and then 1, 1, 2, 3. The 1 here, 1, 1, 1, 1, 2, 3, and then 0, 1, 2, 3, and lastly 1, 1, 2, 3. Okay, so similarly, repeat this 4 times. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay? How do you detect and correct errors using repetition codes? Now, suppose that the code, we have a code wherein each bit is repeated thrice. And suppose that this is your intended message. So if there is no error, you should be able to get this message. Now suppose, of course we know that there's a noisy channel. This is what you received. Okay? We want to know what is the original message. Suppose we do not know that this is the original message, right? However, that's the nice thing about repetition codes. We will just look at the majority. Alright, so let's look at that. So suppose this is the original message and this is the received message. If you look at this, 100, I automatically know that since we used a repetition code, I will know that this one had an error. Majority wins. Okay? Now, take note here, they're not the same, so I know that this one had an error. Alright, and this one also had an error, so I know that that is 1. This one had an error. Majority wins. And lastly, this one, 0 wins. Okay, so now I know that this is now the original message that was transmitted. Alright, so that's how you detect and correct errors using repetition codes. Majority wins. Let's look at this one. How do you decode? The original message here should be, this is 0, this one should be 1, and this 2 here should be 0. But take note, in the previous example, so the original message, because we want to decode what was transmitted are these numbers, but the original message is 010. Understand? This is the um, that's how you decode. Okay. Next, suppose each bit is repeated 4 times. How do you decode this? So this one has no error. This one should be 1. Okay. And now that's the problem here. There's no majority wins here because you have 0 here and 1 here, you know. So that's the problem when you use an even number. You do not know whether it's you do not know if it's 0 or 1 So you do not know if the message intended was this is 0 1 1 or 0 1 0. Understand? Okay, now let's now go to Hamming codes. The Hamming distance between two code words is the number of bits where the two words differ. Alright? And the Hamming distance is denoted by d of x, y. Okay, so let's look at this. What is the distance between these two code words? They differ on the first, on the second, and on the third digit, right? They're only the same on the last digit. So therefore their distance is 3. Now here, one first digit is okay. Second digit, not the same. Third digit is okay. Fourth digit, different. And then this is correct. Okay, so they vary in 3 positions. Or just by looking at it, these are all ones. And this one has 3 zeros in it. So their distance is 3. Now, suppose that the message sent is X and Y is the message received. If the transmission was error-free, then we would have X should be equal to Y. But then again, we do not expect to get that. Okay, so the question is, again, the problem of coding theory. How do we detect and how do we correct the error so that we can recover X? So in order to do that, we use this nearest neighbor decoding. So what we do is first step, compute the Hamming distance between the received message and each of the code words in our code C. And then we take the code word of minimum Hamming distance from Y. So meaning to say the nearest, okay, the nearest neighbor. So that's why it's called nearest neighbor decoding. So for example, this is our code. This is the set of code words. And the message received is this one. So just by looking at your code words, although again you should compute, no? But just by looking at your code words, what do you think is the original message? The original message is the third code, correct? Because just by looking at it, it has a distance of 2, right? Whereas with this one, what's the distance? You have 4, you have a distance of 6. And whereas this, in this case, the distance is that 6? This one is also 6. Correct. So this is the nearest neighbor. So that's why we know that that is the original message. Okay? Now this is the representation. So we know that this is 6. We already know that 6 and this is 2. This is the how we represented it, right? So this is the Y that we received and this one is the nearest neighbor. It is closest. It has a distance of 2. But from these two code words, it has a distance of 6. Next question that we have is how many errors can we detect and how many errors can we correct if we use this? Now, first, let us define the meaning of minimum distance of a code. In the last slide, we discussed the meaning of distance of two code words. Now, what we want is the distance of a code. What is that? That is the smallest distance between any two distinct code words. So for example, you have this code here. When we get the distance of this from of the first code word to the second code word, that's 1. And then the first code word to the third code word, that's also 1. And then the second and the third, we just get all the possible distances between any two code words. The distance is 2. The smallest of this is 1. Okay? So therefore, that's what we call the minimum distance of C1. Okay, let's suppose that you have a code with minimum Hamming distance 2e plus 1. This is the answer to our question. It is possible to detect up to, so for the detection, 2e errors, but we can only correct up to e errors. Let me illustrate what that means. So very important here is we have to write it first in the form 2e plus 1. Okay? So we have 15 equals 2e plus 1. What is e there? So when we solve for e, transpose 1. Okay, so we have 14 equals 2e. So our e is 7. So therefore, how many errors can this code detect? We can detect 2e or 14 errors. How many errors can this code correct? Up to 7 errors. Okay? What if we have this one, 20? So similarly, we have this is 2e plus 1. What will we get in this case? So we have 19 equals 2e. E is 19 divided by 2. So that's 9.5. Correct? So how many errors can this code detect? So the answer is 2e or 19. How many errors can this code correct? Of course, we cannot say e because e is 9.5. So we say it can correct up to 9 errors. Understand? The smaller. Okay, so here let's look at a summary. So we have here a few of the um, first few numbers for the minimum distance. So remember that we have to write them in the form 2e 2e plus 1. Okay, so in this case, our e equals 0. Here, e is equal to 1 half. Here, e equals 1. Here, e is equal to 3 halves. And lastly, here, e is equal to 2. I will leave it up to you to verify that these are all the values for e. You just have to solve the equation 2e plus 1, correct? So remember that here for detecting we have 2e, right? So that's why you have 2 times 1 half, you get 1 error detecting, but of course you cannot get one up to 1 half error. It's not possible. So here you have your 2e here is 2, your e here is 1. Here your 2e is 3 and your e of course is up to. Remember the word up to. So since your e is 3 halves, you can detect up to 1 error. 1 error. Okay? And here your 2e is 4, your e is 2. Okay? Alright, so let's now turn our data into Hamming code. So suppose we want to transmit this 4-bit. Okay, so what you need to do is to first write down the powers of 2. Powers of 2 would be 2 raised to 0, 2 raised to 1, and so on. Correct? Okay, so what you need would be, what we will do here is to add digits, not append, sorry, but yeah, add digits. Okay, so for the powers of 2 positions, so we have P1, this is 1, 2, 4, 8. So we have P1, P2, P4. These are the powers of 2. And then for the remaining, I'll make it green. So these are for the data. Oops. This is D3, D4, D5, D6, D7. Okay? So the data positions, that is where you write your data. So for our data position, we have 1, 0, 0, 1. So basically, you skip the parity positions. And what are those parity positions? The powers of 2 positions. Okay, so what will happen here is, so for P1, this means check 1, skip 1. For P4, that P2, I mean, it's P2, P2, check 2, skip 2. For P4, check 4, and so on. If you still have P8, then that means check 8, skip 8. Now take note that you all start, whenever you check, you always start at the parity position. Here, start at P2. Here, start at P4. And our goal is to always have even parity. Okay, so let's do that. For example, for P1, starting with, so here, start at P1. So start at P1, check 1, skip 1. Check 1, skip 1. check 1, skip 1. Oops. Okay. So, what do we have there? We have P1, 1, 0, and 1. Since what we want is even parity, P1 should be equal to 0, correct? So P1 is 0. Let me just erase that. Next, we will now check our P2. So for P2, start at P2. Start at P2, check 2, skip 2. So start at P2, check 2, skip 2, check 2. Am I correct? Yes. So what do I have there? Question mark 1 and then 0, 1. So again, we already have two ones here. So P2 must be equal to 0. Okay? Because we want even parity. Next, let me erase this. Okay. So, let me use orange. Okay. So for P4, start at P4. Check 4, skip 4. 1, 2, 3, 4. There you go. So, therefore, P4 should be equal to 1. So, this is now that's how you turn your code, your 4-bit code, into your Hamming code. Okay? Now, let's do the opposite. So, suppose that we received this this 7-bit Hamming code. We want to find the original byte transmitted. What is the original code that was supposed to be transmitted? Okay? So, and of course, if we want to find the original code, we want first to detect if there is an error and correct what would be the error. Okay, so let me just write my numbers here. 1, 0, 0, 1, 1, 0, 1, and then I will write down the positions. Okay, so this is P1. These are P, right? Parity positions D3, P4, D5, D6, and then D7. So what we will do is, just like in the previous slide, we will check all the parities. So let's check P1. So check 1, skip 1. 1, 2, 3. Okay. So we have 1, 0, 1, 1. Okay, so you have odd parity here. So that means P1 has an error. P1 has error. So P1 should be equal to 0, right? Next, let's go to P2. So for P2, check 2, starting at P2. Check 2, skip 2, check 2. So what do we have there? 0, 0, 0, 1. Again, you have an error because this has an add parity. So therefore, P2 has error as well. And therefore, P2 should be equal to 1. It cannot be 0. Okay? And lastly, let's look at P4. Let's check P4. Check 4, starting at P4. 1, 2, 3, 4. So we have, again, error. 1, 2, 3. Right? You have odd parity here. So P4 also has error. So therefore, P4 should be equal, it should not be equal to 1, but P4 should be equal to 0. Now, what is now the error here in the data? Okay, supposedly the data here or so in this case, the original data would be 0, the D3, D5, D6, D7, right? So that would be 0, 1, 0, 1, 0, 1. But this one has an error. Okay, so what is the original data? How do we correct it? If you look at the errors in parity position, what you just need to do is to add. So you have 1 plus 2 plus 4. So that's the you add the parity positions 1, 2, and 4. So that would give you 7. So that means D7 has the error. Okay? So therefore, D7 should be equal to 0. Okay? So this one must be 0. So the original data should be 0, 1, 0, 0. Remember, you are looking at your data positions. D3, D5, D6, and D7. You have 0, 1, 0, 0. Okay. Let's now go to error detection and product tagging. So product tagging is used for easy identification of products as well as for tracking and inventory purposes. You usually see this in grocery stores. So most common types of transmission errors would be single digit. So like for example here, the 4 became 9. Transposition, that means two numbers got interchanged. Jump transposition, so here the two numbers got interchanged but they jumped at something. Like in this case, they jumped this digit here for twin, so that means here 5, 5 here became 3, 3. 5 was read as 3. Okay, and then phonetic. So, okay, phonetic. 30 became 13. So, probably also 17 becomes 70, something like that. Jump twin here means 3, 3, and then you skip a digit, but then there's a twin there. Okay? So, Universal Product Code or UPC. So, these are the barcodes that were created to help grocery stores speed up the checkout process and keep better track of inventory. So, these are the UPC that you see in product. So, this is an example. That's decoy. Okay, so let's now look at the 12-digit UPC. So you have 12 digits, so X1, X2, up to X12. Let's just name them like that. Now take note that for the first digit, it refers to what it refers as to what kind of item is that. Is that general grocery? Is that meat and produce, drugs and health products, non-food items, coupons, other items? Okay, and then for 1, 8, and 9, they are just reserved for future use. And then for the rest, so for example here, the first number is 0. So in our previous slide, that would be general grocery, right? And then the next 5 digits, it represents the manufacturer. Okay, that's the company prefix. This is the item reference number for the next 5 digits. And then for the last digit, we call that our check digit. We will learn how to get the check digit. Okay, so in order to get the check digit, we follow this rule. So take note that you have 3 times the first digit. So what happens here is that for the odd positions, you always multiply it by 3. Okay, and then you add it. Then for the even positions, you just add it by itself. And then we add everything, and then we find them modulo 10. Now, what is the meaning of modulo 10? So let us recall that when we do something modulo 10, that means we just get the remainder when divided by 10. So for example, I have 33. Modulo 10, what is that? That's just 3. Correct, class. So basically, since it's modulo 10, you just get the last digit. For example, if it's 17 modulo 10, what would that be? That's 7. Understand? Okay. Um, so again, I just have the slide here for modular arithmetic. We already discussed this in the first module, right? When we did our patterns. Anyway, so let's just try if you still remember your modulo. So is 75 congruent to 15 modulo 10? So from our definition, A is congruent to B mod 10 if A minus B is divisible by 10, right? So 75 minus 15 is equal to 60, and that is, yes, divisible by 10, right? And take note that both of them, modulo 10, would just be 5. Okay, we always want the smallest number. Okay? The smallest number, when we're talking about modulo m, when we find the smallest number, we want, let's say this is x. We want x to be 0, 1, 2, up to m minus 1. Because remember that we want the remainder. Diba? When you get the remainder, when you divide it by m, it has to be less than m. Okay? Anyway, let's look at this one. 78 congruent to 10 mod 7. So 78 minus 10, that is 68. And 68 is not divisible by 7. So the answer is no. Alright, so we have here an example of, this is a UPC. Let's check if it really satisfies this one. So our 3, so our position, so 3 times 0, right? Plus 7 plus 3 times 7 plus 3 plus 3 times 3 plus 0 plus 3 times 3 plus 4 plus 3 times 4 plus 5 plus 3 times 1 plus 7. Okay, so take note that these are my odd positions: 0, 7, 3, 3, 4, and 1, right? And take note that here, they all have, they're all multiplied by 3. And then for the even positions, just stay as is, okay? Now, since we do not want our numbers to become big, we can just automatically turn them into modulo 10. Okay, so for example here, so 3 times 0 is 0 plus 7. Let me just write everything. 21 plus 3 plus 9 plus 0 plus 9 plus 4 plus 12 plus 5 plus 3 plus 7. Correct? So what I will do here is this. So 0, 0 plus 7 is 7. 21 plus 7 is 28. Plus 3, 31. Plus 9, 40. 49 plus 4 is 53. It's getting bigger now, right? So up to here, 53, you can continue adding. But what I will do if it's already big, here, 53 mod 10 is just 3, right? And then plus 12 plus 5 plus 3 plus 7. So at least it's smaller now. 3 plus 12, 15 plus 5, 20 plus 3 plus 7. You get 30, which is equal to 0 mod 10. Correct. So see? Okay, so it really satisfies this relationship. So what you can do from now on is whenever you go to the grocery store and then you see a UPC, you can try this and check that the numbers really satisfy those. Okay, so this here is another example. I will just you can pause this video and try to see if the numbers really satisfy. Of course, it should satisfy that. Okay, so suppose we want to find x here such that we want to find the check digit so that we have a valid UPC. Let me just get the odd positions. Okay, most of them are just 0, right? So I have 3. Those are the numbers that I will multiply by 3, right? So since I have 0, 0, no need, and then 3 times 1, okay? Then the rest is 0, and then I will add the rest. So 7 plus 5 plus 1 plus 9 plus 1 plus x. This one should be equal to 0 mod 10. So therefore, I have 9 plus 3, 12 plus 12, 24, 25 plus 10, I have 35 plus x should be equal to 0 mod 10. So therefore, what is the nearest number so that this one will be divisible when the remainder is 0? So that the remainder is 0 when divided by 10. So therefore, x should be equal to 5. Correct? Okay, quick response code it is a code. It was in Japan by Denso Wave in 1994. It is designed to allow high-speed component scanning, and it is detected as a two-dimensional digital image by a semiconductor image sensor. Okay, so what happens here is that the sensor locates the 3 distinctive squares here at the corners of the image and uses a smaller square near the 4th corner, somewhere here, to normalize the image for size, orientation, and angle of viewing. The small dots there are then converted to binary numbers and their validity checked with an error correcting code. So what you can do is you can go to this one, QR code generator. I will show you how to use this. So here, what you can do, for example, opens the URL after scanning. For example, I just want to go to gmail.com. Okay, so it will generate this code. So once you scan this code over here, okay, so it will automatically take you to gmail.com. Or if you want to displace a Facebook button, or anyway, shows an image gallery. Anyway, so what you can just try that. Okay, you can put any URL there for a website, and then you can also try this there. Okay, and then when you scan it, it will take you directly to the website.